topic is about capacitance. Typical capacitance is made of two parallel conducting plates, and you can accumulate a positive charge on one plate and accumulate a negative charge on another plate. By storing the charge, you can have E field built in between. And the capacitors are the devices which help us to store some charges. And because they store charges, you have E field in between. You can imagine this device also store electrical field energy for us. Okay? And by definition, capacitance C describes how capable this capacitor is in terms of storing charge, given each 1 volt of voltage difference. If you apply 1 volt of voltage difference, and then the charge is going to accumulate on the two plates until the charge equals to the capacitance multiply the voltage difference you applied. The ratio between the charge and the voltage difference is going to be C, which is not going to change. And that is determined by the shape and the design and the size of your capacitor. Okay? If you have a large area of those plates, bigger area, double the area, you're going to make a bigger capacitance. On the other hand, if the distance between the two plates is very small, you can have a large capacitance. Otherwise, if the distance is very far away, you can have a small. You're going to have a small capacitance. And notice that the ratio between these two, C, is determined by your capacitance design. As long as you do not change A and D and do not add anything else, the capacitance C is not changing. Then, by doubling the voltage difference between the two plates, you're going to double the Q. Or if you reduce the Q, you're going to reduce the voltage difference correspondingly. The ratio stays the same. Rearranging this equation, if we know Q and C, we can calculate voltage. Again, it is very important to be consistent with your subscript notation. This only applies for a particular capacitor, using its own charge, not the total charge, not other people's charge, and finding out the voltage across that particular capacitor. Okay? And also notice that here, whenever we talk about delta V related to capacitor, we talk about the absolute value. Don't worry about this low voltage minus high voltage. We always consider the voltage to be positive, the absolute value of this minus that. Okay? Then rearrange this equation, we can also see that if we know the voltage difference between these 2 points, and we know the C, we can multiply voltage difference with C to figure out the amount of charge on that capacitor. And then, instead of one capacitor, we can have capacitors combined in series and in parallel. And keep in mind, very, very importantly, when they are combined, capacitors are very different, exactly opposite comparing to the resistors. When you are making capacitors in parallel, as you can see here, 1, 2, 3, they are in parallel. And again, because they are in parallel, we know the voltage here, here, here is the same. The voltage here, here, here are the same. The voltage difference between these 2 points, this 2 points, and these 2 points, they are all the same. They share the same voltage difference. And then each one is going to have Q, positive Q here. The voltage multiply Q1 and the positive Q here, maybe a little bit less, and even less if it's getting smaller. Okay? However, all this combined in parallel, it's equivalent as if you have one large plate on top, which has positive charge and one negative charge plates at the bottom. And then it is connected to the battery. Okay, and now you have the equivalent, C equivalent. And then because your Q1, Q2, Q3 are the same. Sorry. Your voltage 1, voltage 2, voltage 3, they are the same. And the Q, all these top plates adding together, the total Q equals to Q1 plus Q2 plus Q3. Because that equals that equals that equals that. Then you are having, as if you have a giant capacitor, the equivalent C is equal to C1 plus C2 plus C3. This equation, multiply the same delta V, delta V, delta V. You're going to have the total charge and the charge 1, multiply delta V, charge 2, and charge 3. When they are in series, the charges add together to give you more. And the capacitors add together directly, capacitance adds together when they are in parallel. That's exactly opposite from when you're combining two resistors in parallel, okay? What happens if you make them in series? As you can see, when they are in series, you apply a certain amount of voltage in series, and then it's not that each one of them have a voltage difference equal to the total voltage. Again, through this loop, we have the voltage change first time, delta V1, and the second time, and the third time. 3 steps of voltage change adding together equals to the total voltage change. And which one is bigger, which one is smaller, how big is that? We don't know for sure, but we know that's how they are related. Here, when they are in parallel, they have the same voltage difference for each one. Here, they do not have the same voltage difference, but step 1, 2, 3, different steps of voltage adding together equals to a total voltage. That's the same when you combine resistors in series. However, if we look at each individual ones, C1 has a Q1, C2 has a Q2, C3 has a Q3. Notice that this part which has a negative charged plates and a positive charged plates. This part is not connected to any other things physically. So you know that Q2 and the negative Q1 together must be 0. Why? Because in this region that I just circled, this region all together is neutral. If you have this much positive charge here, that means you are leaving the same amount of negative charge on the other side. By looking at this, we know Q1 has to be equal to Q2, has to be equal to Q3. So when they are in series, voltage may be different. Voltage adds together give you the total voltage. However, each one of them have the same Q1, Q2, Q3, and that's equal to Q total. And this is as if you have a capacitor which is combined together. That's your battery. Okay, and that's your C equivalent. And the equivalent capacitor is actually, later you're going to find out, combining this way is going to be smaller than any one of them. Okay, and if you are using your equivalent capacitance, multiply the total voltage difference, delta V total equal to epsilon, the battery voltage, and you are going to get the total charge. And again, your total charge is the same as Q1, Q2, Q3. And in this way, they add reversely when they are arranged in series. Okay? So if you have two capacitors, one very large, one very small, added in parallel, you are going to get a total equivalent capacitance even smaller than the smaller capacitor that you are using. Okay, what's going to happen if you have one capacitor, okay? If you are increasing the area, your capacitance is going to increase. That means giving the same amount of voltage difference, larger area, you store more charges. But if you are increasing the distance, and then you're going to reduce your capacitance, increasing the distance, making your capacitance decreases. And that is because the voltage difference, the absolute value of the potential difference in between, is equal to E multiplied distance. If the charge does not change, but you just separate them further away, making them a bigger distance, the E field is still the same, but a larger distance, meaning a larger delta V. Delta V equal to E multiplied D. And then a larger delta V, same Q, gives you a smaller C. Okay? So C is determined by the geometry design. Bigger area, bigger C. Smaller distance, bigger C. So what's next? If we are using this in the circuit, there are two different ways. One is that you are making your capacitor keep being connected to a battery. Later we know once it's connected to the battery, it takes a small amount of time for the capacitors to be charged. Once it reaches a steady equilibrium situation, when it is keep connected to a battery, you have some golden rule that the delta V of the capacitor equals to the battery voltage. And this stays no change. And that's important when you are dealing with any problems which says that the system is being connected to the battery. Then you have a voltage does not change. If your voltage does not change, and then you increase your C, you're going to have more charge. You decrease your C, you're going to have less charge. When it is keep connected to the battery, the voltage stays unchanged, and the Q may change if C is changed. When you move them further apart or do something, the battery voltage maintains the voltage of the between the two capacitor plates, and the charge may change. We don't know. It's connected to a battery, so it can keep adding more charge or get rid of some charge. However, in a different situation, when a capacitor is disconnected from a battery, so it's a positive charge here, negative charge here, okay? It's already charged. And now it is disconnected from battery. It's not connected to other objects. Then you can still make them further apart or do something to change the C. However, in this situation, the golden rule says that the Q can't move. And the Q is going to stay unchanged. Okay? And then, however, it's not maintained the voltage difference by a battery. In this case, the voltage difference delta V may change when C changes. Okay, let's give you one example. In a disconnected case, for example, okay, it's disconnected. Okay, if D increases, if we are making a distance to separate further apart, what's going to happen? C is going to increase, smaller d, larger C. And if the C increases, Q equals to C multiplied delta V. And delta V equal to Q over C. If the charge cannot move, it's disconnected, you still have that amount of charge not going anywhere. Charge is the same. C increased, Q stays. That means your voltage between these two plates, delta V, has to decrease. No, sorry. If you decrease the distance, C is going to increase, Q is going to stay, and the voltage difference is going to decrease. Okay? So, reversely, if D increases, we're going to have C decreases. Increasing D, decrease your C. And the Q still remains the same. Increasing your C, we're going to have delta V voltage decrease. Okay? Next, let's look at the energy saved in the capacitor. The energy saved there is equal to half of the voltage difference multiplied the total charge on one plate. There is a half because you do not have all those charge initially to start with. You did not move all the charge at once. It gradually increases from 0 to the maximum amount, and such integral gives you a half. And the half voltage multiplied charge, that's the total energy between the two plates saved in the capacitor. This is going to be equal to, consider delta V equal to Q over C. This becomes Q squared over 2C. Also consider Q equal to C multiplied delta V. This becomes a half C delta V squared. Okay, now if you would like to compare this situation, capacitor C1, C2, C3, which one saves more energy inside? Then we should look at this equation. Why? Because 1, 2, 3, they have something in common. That's the voltage difference, delta V, are in common. When delta V are in common, same value, then you compare the bigger C1. It's going to give you a bigger energy saved in the bigger, higher capacitance. Okay? On the other hand, if they are in series, which one is going to have more energy stored? In this case, delta V1, delta V2, delta V3, I don't know which one is higher. However, I know Q1, Q2, Q3 are the same. If Q are all the same, we consider this equation. Q and Q squared, they are all the same. We compare C. A larger C is going to have a small energy stored. A smaller C is going to have a more energy stored. Okay? This can also be used when you consider this. Here, in this situation, if your Q is fixed, not changing, and your capacitors C reduced, Q stays unchanged, C reduced, in that situation, your energy is going to increase. Why? Q stays the same, C reduced, this value is going to increase. Okay? So what happens if you have a pair of capacitor? It's disconnected from other things. We cannot add any more charge. The charge stays not going anywhere. However, the separation D becomes bigger. C reduces and the energy increases. Where did the energy come from? Keep in mind that there's a positive charge and negative charge. They are attracting each other. By separating them further apart, somebody like a Spider-Man or whoever needs to do some work. And that work increases the amount of energy in between. And it's going to increase the amount of voltage saved in between. Okay? By the way, this is, no. When you have distance increased, you have C decreased. When you have C decreased, and the Q does not change, your voltage increased. Again, your E field did not change. Distance increased, your voltage increased. The voltage difference increased, and the total energy increased. Q did not change, C increased, the total energy increased. Where did this energy come from? Whoever separated them further apart has to do some work. That's where the energy comes from. And also, just a quick reminder, in some problems, you may need to recall the absolute value of the delta V equals to the E field multiply the distance in between. That's uniform E field in between. And also the E field is equal to, using Gauss's law, we can find out the E field equal to the charge density on one plate over epsilon 0. And that is equal to Q over A over epsilon 0. If you do not increase your charge density, you do not change your E field. However, if you are making more charges, you are increasing your E field. And then we are interested in not only the total amount of energy, but also what about the total amount of energy saved in between the capacitor plates divided by the area and the D. Area multiplied D is the volume. The total energy divided by the volume gives you the energy density. And that energy density is equal to a half epsilon E squared. That's determined by how strong the E field is. If the E field is strong, every centimeter cube, you have more electrical energy stored. If you double the E field, you're going to make your energy density 4 times larger. One last word about this is that if we add dielectric chi instead of using vacuum or air in between, we are going to make some dielectric insulated material, not conductor, in between the 2 plates. What's going to happen is that we're getting a new capacitor which is equal to epsilon 0 A over D. That's what you have when you have a vacuum in between or air in between, and that multiply chi. When we add a dielectric, we are increasing the amount of capacitor. And then once you have your capacitor increased, then given the same voltage difference, you can save more energy. Given the same voltage difference of battery, you can save and store more charges. Okay, and that's it. In some of the homework problem, when you have a system of 2 capacitors in parallel and then disconnected with the other things, then you know voltage may change. You have no control. Charge is not going to change, but if you have 2 of them disconnected from anything else, okay, then your charge 1 and the charge 2, they may redistribute. However, charge 1 plus charge 2 equal to charge total, that's going to stay the same as long as these 2 capacitors are disconnected from other objects. Okay, so that's the end of reviewing for capacitors.